Doing more Net Plus. This is the second half of Net Plus today, Module 4. So I've got the slides here. And let's take this stuff. A rapid review of network protocols. So wide area network protocols you have a physical topology of how they're lined up. Now you might have locations of your company, typically not single computers, but you might have locations of your company connected one to the other like this. And if a cable breaks, then it breaks the whole network down. That's a bus. A tree or hierarchical network is like this, where you have something at the top that goes to a few of these, and these split to more. And now you have a root that controls everything, and it's a hierarchical system. And then you can have a ring, which Token Ring has, and Fiber Channel and many others, or Fiber FDDI, Fiber FDDI, and other ones. There's a ring like this, so if the cable is broken in one spot, you can still communicate by going the other way around the ring. It can survive one break if it's a double ring that has cables going in both directions. And then there's a star, which is what Ethernet uses. You have a central switch, and every device has one cable going to the switch. And if a cable breaks, it only causes one device to lose connectivity. Token Ring had this physical wiring layout, but it was logically a ring. It would have a token sent to each device going around in a circle, and you could only send network traffic or receive it when the token came to you. So there was no issue of collisions. You had to wait your turn to speak. And what you have on large-scale internet is a mesh. A full mesh is where you have every possible connection, and you cannot do that with any large number of nodes. It becomes a ridiculous number of connections. And here's a partial mesh where you have more than the minimum number of connections. So if one breaks, most of the time you'll be able to find a way around. Is the FDDI ring token only? I do not know if the FDDI ring used tokens. It's a good question. I've never heard that it does, but I've never used it. I've just read general terms about it. It's a very old network.
The mesh is getting used a lot in the CPU.
Inside a CPU, they use a mesh? Oh, for the bus?
Because there's a whole bunch of cores.
Oh, to communicate with among cores. I didn't know that. That's interesting. Good. All right. Anyway, let's take a look at
It's going backwards.
a Kahoot, I think.
All the new technology, all the new product use the old technology.
Well, I think we've already done that for E before. We'll just go on to 4F. I think somehow, yeah, that's right. I ended up, all right, anyway, so I thought we already talked about that. So, wait, here's what I wanted to be. All right, so T1 and T3 lines are American. The FDDI ring, no, I don't think FDDI rings are used today. I think only legacy, the leftover from decades ago. Nobody would install a new one today because it was only 100 megabits per second, so they're not cost effective anymore. So T1 is actually originally was just a bundle of 56K copper wires, although now it's mostly over fiber. So this gives you a 1.5 megabits per second dedicated circuit from you to your internet service provider. You have a single cable just for yourself and two-way traffic. And T3 is 45 megabits per second, and the European version is similar, E1 and E3. These are internet connections you can purchase if you want a lot of bandwidth. Or you can also get fractional T1s or fractional T3s where you're just getting part of the bandwidth of a cable which is shared with other people. Sonnet is what you get if you want to have a really high-speed network connection. Synchronous optical networking, it's all over fiber and a ring network, and you can get up to ridiculously high internet speeds and pay tens of thousands of dollars a month for it, and this is what you get if you're like a data center with a whole bunch of powerful servers or something. Frame relay is a layer 2 protocol that is intended to make it possible for multiple connections to run over the same physical wires. And you create these virtual circuits, so it is as if you had a wire going from one location to another with a certain bandwidth, but in fact they're all sharing the wires. And this, so a frame relay is a way to split up something like a T1 or a T3 into chunks. And frame relay, more frame relay. So you can create these permanent virtual circuits that are always connected, or a switched virtual circuit that connects only when you're using it and disconnects when you're not using it. And it addresses them at these things called data link connection identifiers. X25 is an older protocol that people used up through the 90s. It's pretty much gone now, but it was like frame relay, an earlier version. And ATM, asynchronous transfer mode. This is still, I think, used quite a lot today. Everything has 53 byte cells. So you have 5 bytes of address and 48 bytes of data. So very little packets move rapidly, and you can interleave a lot of different packets on it. So, all right. Used to be SDMS is an older version. Multi-protocol label switching. This can forward WAN data using labels instead of just IP addresses or something. And so you have a shared cloud network that can carry many types of traffic inside it, and the traffic decisions are made on labels. Label switching can be much better than routing by IP address. It can be much faster. What's the BW with ATM? I can be very fast, I think. I think it can be very fast, but I don't know the number. Wasn't in your book, I think, but I think it can get quite fast, quite a lot of total bandwidth. All right, and then there's SDLC and HDLC, synchronous data link control and high-level data link control, and this is another layer 2 protocol. All these things run at layer 2 to get from your location to your ISP or within your ISP, and so you have a primary node pulls to secondary nodes to request their data like token passing, and this one here has error correction and flow control, and 3 modes of HDLC. It has normal response mode, asynchronous response mode, and asynchronous balanced mode, which just have to do with how it handles who gets a turn to speak. So sort of like the more complicated upgrade of Token Ring. And then there are converged protocols, is what you often do. Remember, your ISP is carrying many kinds of traffic over the same wire, and pretty much everybody is now. Your telephone traffic and your email and everything's going over the same wires, so you have multiple services running over the same network. They call that converged protocols. So DNP3 is an open standard used by the energy sector for interoperability between SCADA and smart grid applications. SCADA is supervisory control and data acquisition. Devices, these are devices in industrial factories that control equipment over the internet. And then there's the smart grid technology, where everybody has smart power meters at their house, which can regulate the flow of power and communicate with other devices to try to improve efficiency. All right, I see, good. Yeah, all right. And so this is a multi-layer protocol that could be carried over TCP/IP or something else. And the more recent versions of it have authentication, but the original specification was vulnerable to spoofing and replay and had only pre-shared keys. The current standard is up here, this IEEE 1815-2012, that supports public key infrastructure, so it can have encryption like HTTPS. And then there's storage protocols. You can have a server array, many servers that are processing, and you can have a storage array, which is many servers that are just storing data, and this is all over the place now. You have a storage area network, and so the storage devices themselves have to have a way to move traffic among the devices, and so this is called fiber channel, and fiber channel does not necessarily use fiber optics. It's called a fiber because you have many parallel lines connecting the device to another to move a lot of data, but you can put it over Ethernet. That's fiber channel over Ethernet, and then that is the internal network used to communicate among the storage devices. And you can use iSCSI also, and that's for storage area networks. And the point of this is you can have block level file access over a network, so you can typically put things like virtual machines on these, and you load the virtual machine into memory from the storage area network. You just access it from your computer like a hard drive, but it's actually over a network connection. It's a virtual hard drive loaded block by block from a storage area network. So fiber channel over Ethernet, fiber channel use special cables and hardware, but yes, and Shu says there's lots of new protocols to improve the bandwidth and latency of the storage servers, and I'm sure there are. A lot of this stuff is not very up to date. This is the fundamentals, but yeah. All right, then host bus adapters, fiber, this uses standard Ethernet, but not TCP/IP. Remember, Ethernet is layer 2, so it's frames, and fiber channel over IP is another way to do it. You can actually put it over IP if you want to. Wouldn't a SCSI-based VM be slow? Well, the SCSI is just how you connect to your hard drive. And I don't know, there was a time when SCSI was considered fast. I think it's no longer considered fast for a normal computer. Now I think you're right. It probably would be slow by modern standards. And then there's iSCSI, however, and this allows you to access storage over a wide area network, and it uses logical unit numbers to address the storage units. And there's virtual storage area networks. Used to do proprietary hardware and software, so you can have a virtual storage area network like a virtual local area network, and this is what they call software-defined networking. As the servers become virtual, the switches and firewalls become virtual, and the hard drives become virtual, so everything is just a virtual system that is different than the actual physical hardware underneath it. All right, now 25 gig or above NICs are called smart NICs and handle storage and network of a server. Oh, good. Good information in the chat there. All right, then there's Voice over Internet Protocol. This is used to make telephone calls over the internet, and there are two protocols. Real-time Transport Protocol is what carries the audio and video. Session Initiation Protocol is what rings the phone and tells whether it's picked up or not. So, and there's a secure real-time protocol, which uses encryption, because this by default can be run with no encryption. And usually people do turn off the encryption to get high-quality sound, but it's safer to have the encrypted version. And so voice over IP saves money at companies. Was the original idea that you wouldn't have to pay for separate phone and IT wiring. In practice, what I heard from Cisco professional installers is it doesn't actually save money, but people do it because you get a lot more features. Now your phone can be smart. It can have press 1 for this, press 2 for that, and forward the phone call at certain hours and all these fancy features that you don't get with a normal phone. So anyway, it does mean that your telephone traffic can be attacked with network attacks. And I mentioned RTP gives you no security by default, and I've done a lot of times use Wireshark to just eavesdrop on a telephone call that's not encrypted. All right, and so software-defined networks are where you have, you separate the control plane from the forwarding plane. This is one way to look at it. So you don't have, your control plane makes routing decisions, and the data plane forwards routing packets through the router. So with software-defined network, you can make routing decisions in a virtual way. The point is you're not connected by your hardware. In the early days, you would have a switch, and all the computers in one room would be on one LAN because they connect to that one switch. But now we have virtual LANs, so you can label each computer, and it is, even though many computers in many different buildings are grouped into one virtual LAN, they share layer 2 broadcast traffic, and you can also do this at layer 3 with IP routing, and that's the point. Software-defined networks allows you to define your networking in a virtual way without much regard to the actual physical network connections. And it's more and more popular. So the most well-known software-defined networking protocol is OpenFlow, which allows a central controller to control the switching rules and uses encryption. So that's what you would use to organize that virtual network traffic. And this, I think, is what we're actually using. If you use something like, say, Amazon Cloud or Google Cloud, they give you a virtual server, and they give you a virtual firewall and a virtual router to put it behind, and all that stuff is simulated and not tied to any one physical location or anything. In fact, this was a big issue when Microsoft Azure came out. They said, we can't even tell you what nation your data is in. It's just somewhere in our cloud. And when people got upset about that, they had a more expensive tier where you can be guaranteed that the data will stay in the United States. You might need that for compliance. All right, now let's take a look at 4F. This is the right Kahoot. All right. Oh, there's the number. Okay, 889 1282. All right. Cupcakes, maybe?
Okay.
Mooncakes? What are they? Hard to see. Was I able to lower the timers? Oh, I don't know. I forgot to check. We'll see. We'll see if there's a problem. Yeah, this is, yes, this is F. All right, let's give it a shot. All right, so which link goes up to 45 bags? That's a T3, another Net Plus question. All right. All right, which one is a storage protocol? All right, that's fiber channel over Ethernet. All right, what protocol is used by the energy sector? All right, DNP. All right, the most well-known software-defined networking protocol. All right, OpenFlow. Hello, Jalilham. All right, so let's record the winners. All right, see who that is. Rouhani. All right, so let's talk about wireless networks. One problem with wireless networks is one device can create DOS attacks. One thing you can do is just have like a noisy motor that puts out a lot of electromagnetic interference, and that will stop wireless transmissions. You can also send deauth frames, which will cause connections to be broken. It basically hangs up on them, and there is no known defense against these problems. It's a weakness to the protocol. Now, there are certain bands available that you can use without a license from the Federal Communications Commission, and so all kinds of consumer electronics use the same bands and they interfere with each other a lot. The two most common bands are 2.4 gigahertz and 5 gigahertz. There are techniques to try to move your traffic through this crowded, noisy band. And yes, 6 gigahertz as well is the new one, yeah. Anyway, frequency hopping spectrum hops across many channels. Direct sequence spectrum spreads the signal across a whole band, and orthogonal frequency division multiplexing can be used in radio and also in fiber, where you use independent signals that do not interfere with each other to carry multiple channels of data. All right. And so here's the various generations. The earlier versions were like 802.11a and B and G were pretty slow. And then 802.11n was probably the most common one now, Wi-Fi 4, and now we're moving into 5 and 6 and 7 gradually. That can go up to gigabits per second. All right. And so I wonder if we got that 6 gigahertz. Yeah, here's the radio frequency. Like you said, originally it was just 2.4 and 5, and now the latest ones, Wi-Fi 6 and 7, can also use 6 gigahertz. Yeah, apparently 60 gigahertz. Yep, that's another one. Yeah, 70 to 90. Good, you guys know your ham radio rules better than me. I knew them long enough to pass the exam, and I don't remember it all, the bands that you're allowed to use. All right, so there's 4 modes of a wireless network card: managed, master, ad hoc, and monitor. A managed mode is the only thing normal laptops use. Your NIC is a client, so it connects to a master, which would be your router, your Wi-Fi router, and the router tells it what to do. The router says, I'm handing out traffic on this channel at this rate, and your managed mode just obeys that. So this is typically the only mode you normally use. You have the master mode on the access point and managed mode on the clients. That's all normal people use, but it is possible to reach these 2 other modes. An ad hoc network is where 2 laptops would connect together without a router. point-to-point like a crossover cable. That's an ad hoc network. And monitor mode would be used only by network engineers or hackers, where you sniff WLAN traffic, including all the traffic that is not intended for you. Because as I mentioned before, because the radio traffic is not directional, then this means that everything you send on a wireless network goes to everybody in range. And so you can pick up traffic intended for other devices that was not intended for you. And yeah, it did look like the thing froze up for a minute there. Yeah, it looks like maybe it's still frozen up. Let me go back to here. Oh, yeah. Turned red on me. I guess I'll try disconnecting and reconnecting. Let me try this. All right. It is reconnected. I think I'm going to have to stop the streaming and restart it. Here it looks like, okay, I think I'm back up. Yeah, something went wrong with the network. I had to turn it off and on again a couple of different ways, but now it's showing green. So let me know in the chat when you can see this. It's looking better here now. It's back. That's what I thought. I could see here. There's an indicator. Something went wrong with the City College network, but just disconnecting and reconnecting brought it back. All right. So ad hoc networks are where you just have two laptops that talk to each other wirelessly without having a router. So it's a local network between 2 points, like a crossover cable. And monitor mode is where you sniff all the traffic that comes in, even if it's not intended for you, even if it does not match your MAC address. So this would be a way to snoop on what other devices are sending to each other that is really not intended for you. And so the hardware can do this, but a lot of software and drivers do not provide it because it's not something a normal person needs. All right, the SSID is the name of the network. You go into a coffee house or something, you'll see this list in your operating system wireless connection pane. This is the network name, just an alphabetic name, alphanumeric name. It can be anything you like. This is broadcast frequently, and you can turn off the broadcasts to hide your network so it doesn't appear on the list. But if you do that, then if you try to make a larger network with several access points and let people roam, they can't roam because it uses the beacons to tell when you're moving away from one access point and moving to another, and it's time to switch over to that one. So hiding this is a pretty lame security feature. Some people recommend it, but it doesn't really protect you very much. If people are using the network, then you can use tools like Wireshark or Kismet to detect the traffic, even if it's not advertising beacons. And get in. Another weak security measure is filtering by MAC address. The MAC address is sent unencrypted in every frame, so you can just put your NIC in monitor mode and sniff the packets and find out what MAC addresses are allowed, then deauth one of them and take over the connection. But, that's more work than most people. A MAC address will stop people who aren't trying very hard from getting on. If you have MAC address filtering, then people will see it in the list, but when they try to connect, it'll refuse to connect because they have the wrong MAC. So it's something I used to do when I would just use a wireless network at coffee houses, just to stop the people sitting next to me from connecting to my hotspot. WEP was the original encryption scheme for wireless networks. People were reluctant to buy 802.1b wireless cards because they thought it was insecure to use wireless networking, which it is, of course. Your traffic is going all over the place. So they added this encryption and said it would make you as secure as a wired network. That was completely false. It had many flaws in the encryption. It was easily broken, quickly broken, and is not recommended at all anymore. The only reason to use this is if you have some legacy hardware that requires WEP. But if you have a WEP-protected network, some people can get in without knowing the key. I used to have it as a homework assignment in the hacking class. It's not hard to break into at all. All right, so 802.11i defined a robust security network, and this defined WPA2, which is a much stronger protocol than WEP. And it uses AES and this thing called CCMP, which protects it from the attacks that broke into WEP. And WPA has been around for a long time. This was a design for access points that don't have the processing power to implement full 802.11i, so it uses faster, less secure forms of encryption. It's considered weaker, but in practice, any form of WPA is pretty good. There's no major weakness in them like there was in WEP. If you use WPA or WPA2 or WPA3, you have pretty high degree of security that nobody's getting on the network unless you chose a really obvious password or key. You have a pre-shared key in some modes, and then if it's they just have to brute force that key is the only way in that I know. All right. So Bluetooth is defined by 802.15, the IEEE standard. This is your personal area network that communicates between devices like your cell phone and your earphones. It has various versions. All right, it can go 10 meters or up to 100 meters in principle. And it uses a symmetric stream cipher called E0, and this turns out to be a really bad idea. It has a 128-bit key, but in fact the real strength is only 40 bits or so, which is very much like WEP, similar problem. You could in principle have a 128-bit WEP key, but it didn't really have not as much security as you think it should have, and so there are Bluetooth is considered relatively insecure. I'm not sure if the later versions have fixed this yet. Then there's RFID, which are these tags to put on devices that can be scanned with a radio frequency scanner. Active tags have a battery. Semi-passive have a battery, but also rely on the reader for power. And passive ones are powered by the reader, so they have an antenna that absorbs a signal from the reader and then echoes back the answer using the power collected from the reader. And this is the sort of thing you have in the in modern credit cards. We can just wave it past a reader. All right, if you want to protect a device from wireless transmissions, you put it in a Faraday cage or in a metal can. You make a room into a Faraday cage, and then if you work in there, no radio can come in or out because the mesh absorbs it. You can also create a version of this by just having several layers of aluminum foil around an object, or several layers of those pink bags that have conductivity to protect electronic devices from static. All right, let's try the 4G cahoots. All right. Good. I'll give it a few more seconds. How does a hacker guess your MAC ID? Well, they would measure it by just sniffing the network and seeing it's in every frame that's sent. And I don't know what a Cisco. Oh, you're a Cisco. Oh, Cisco is just a maker of network appliances. Doesn't really matter what brand you have. But if you have MAC address filtering, then your only authentication is the MAC address, and anybody can just sniff with a NIC in monitor mode and find out the approved MAC addresses. So it's a weak defense measure. Yes, okay. All right, let's try this. All right, so what mode connects two devices together like a crossover? Yeah, ad hoc mode, good. All right, what technology uses simultaneous transmissions that do not interfere with each other? Yeah, orthogonal frequency division multiplexing. The orthogonal means that these signals do not get mixed with each other. Yes, I see a question about firewalls. Layer 1 firewalls, we'll talk about them more later, I think, but early generation firewalls only filtered by the header traffic and are not very strong. So you have to buy more modern firewalls. Next generation firewalls like Palo Alto are much more powerful. Yeah. All right, and which standard goes on 5 gigahertz only? And that was 802.11a. If it wasn't very popular, it didn't go far enough. 802.11b was the one that really became popular first. All right, and what technology will block a radio signal? Yep, Faraday cage. Good. All right. And good. All right, let's take a look at another one. So, secure protocols and devices. Here's the physical devices at the very level. OSI layer 1 is where you just have physical connectivity, and you could have a repeater that just regenerates a signal to compensate for the decrease in power as the resistance of the wire lowers it. A hub is just a multi-port repeater. So any signal that comes in one port is immediately echoed out all the other ports. It doesn't isolate or the traffic. It doesn't have any security. It cannot send and receive simultaneously. It makes your network into one collision domain. All your devices connect to a hub. Only one device can send or receive at any time. So bridges had 2 ports. So you connect one network to another with a bridge, and the bridge has memory, so it memorizes the MAC addresses at these endpoints, and when it gets a frame, it decides whether it's on this side or that side, and it doesn't send it to the wrong side. And switches are just multi-port bridges. So the switches has a table of MAC addresses in it. It learns all the MAC addresses that are connected to it, and now if this server wants to talk to that computer, it will just send the signal down that one wire and not any other wires, because it knows what devices are connected out each wire. That prevents collisions, and you can connect multiple switches with trunks. Trunk lines are lines that carry the traffic for many devices. VLANs, like I mentioned before, you might want to have a local area network for servers and a different local area network for laptop computers here, or endpoints, and these might be in different buildings. So a virtual local area network will let you put a tag on it, so that even if these devices are in fact not in the same building, they'll be treated as if they're on the same local area network. All right. Port isolation. On a managed switch, you typically limit what's allowed to connect to other devices. Only one port is allowed to communicate to the uplink. This forms a private VLAN. All right, and the idea is you limit with these VLANs traffic. So if somebody takes over a device in one LAN, they can send out packets and infect the other devices. They have trouble getting to this other local area network to infect more devices. VLANs help provide defense in depth. All right. And so port isolation means that, for example, if you go to Starbucks and you connect to the wireless network, and then you try to do like an Nmap scan to see who else is on your network, you will find there is nobody else on your network. Every single customer is put on their own VLAN, so if somebody next to you is sharing a file, you can't connect to it. You can't get to their IP range. This is called port isolation. It separates customers from one another. There are span ports. These are ports that send an extra copy of every packet out that port so it can be monitored, like a mirror port. The problem is, of course, if they're all the same speed, if you have like 1 megabit per second on every port, and you can have a lot of traffic, more than a total of 1 megabit per second going through the switch, and the span port can't keep up with it. So a span port on a switch is a relatively cheap and possibly ineffective way to monitor traffic. What's better is to buy a network tap, a special device just to make a second copy of all the traffic passing through a cable. This is the better way to connect a sniffer or intrusion detection system. And you can set it to fail open, so if the tap fails, the traffic will continue to flow, which is normally what you want. And that can have enough memory to capture traffic bursts and such, so it's more able to follow all the traffic on a high-speed network that has a lot of traffic. Routers are at layer 3, so they can route traffic from one local area network to another. I can get rid of that R if I can get there. There, all right. And it routes traffic based on IP addresses. You can have static routes typed in by a network manager, like static IP addresses you might put on an endpoint. This is what you do with small networks. Larger networks use automatic addressing. And the default route, if you have a leaf network, your laptop is a leaf network. It's an endpoint. You only want one connection going out to the internet, nowhere else. So all you need is a default gateway. Anything that's not local goes right off to the internet. That's simple. That's what you have here. You'd have one device going to the internet, like a router, that has two IP addresses. It has a private IP address, 192.168.1.1, and a public IP address going off to the internet. And the other devices here just define that device as their default gateway, so they can talk to devices on a local area network with 192.168.1 without sending traffic to the internet. And if you have any other prefix, the IP address, it sends it to the router, which will readdress it and forward it out to the internet. So there are routing protocols which automatically adjust the routing table if you have several devices. So you might have several locations connected with T1s and T3s, and if one link goes down, then you want to reroute the traffic. So instead of trying to send it through the broken wire, it will send it through the wires that are intact to get it there. And so that's what routing protocols are for. They're sending traffic through the network, telling the other routers the status of the network so it can make intelligent decisions where to send the traffic. So interior gateway protocols are the ones used by companies, and this is used by private networks. RIP and OSPF are common ones here. And exterior gateway protocols are used for long-range traffic on the internet, and the only one that's used is border gateway protocol, is the one used to route traffic between internet service providers. The original routers had very little processing power and very little memory. They were weak, and so they used a very simple protocol, which was RIP, a distance vector routing protocol. They didn't know how fast the links were. All they did was count how many hops, how many routers you passed through. So if AT&T is 2 hops out port 1 and CCSF is 3 hops out port 2, then it will make a decision to go wherever the less hops are, which is a very simple metric. This turned out to be pretty inefficient. Not only could it often choose the less efficient route because it was smaller hops, but also the updates for networking was so slow that it could get confused, and it could get out-of-date information, and it could send traffic out the wrong way, called a routing loop, where a package would just go around in a loop without finding their way there. That was RIP. Pretty much extinct now, but this is what a routing loop would look like. You go out here, it goes to 141, then it goes to 9, then it goes to 101, 103, 101, 103. Here's a routing loop. It's bouncing back and forth between 2 points without ever getting anywhere, because these guys are confused. This guy thinks the destination must be over on the right. If 103 is on the right and 101 is on the left, 101 thinks the destination is on the right, but 103 thinks the destination is on the left. So they just pass the packet back and forth between them until it times out. That's RIP. RIP was the system that had this problem. Used hop counts. It sent updates every 30 seconds, so it would take a long time to converge. If a network change happened, it could take multiples of 30 seconds before enough updates reached all the devices to converge on the new network. And RIP version 1 used classful networks, and RIP 2 supported classless internet domain routing, which we talked about before with the slash number. So there were techniques to try to prevent routing groups, split horizons, where it would not echo a route back to the router that originated it to try to stop out-of-date information from bouncing around the network. Poison reverse would try to mark bad routes. Don't send any traffic here because this wire is broken. And there was a hold down timer to try to stop it from changing the route too often, because the problem is a bad information would go out and then get echoed by other things and come back to the original one, so it would keep refilling its routing table with the bad information that bounced around the network. So a better solution, and pretty much the only one people use now, is linked state routing protocols, where you have more powerful routers with more memory and a more powerful processor, so they can actually have the whole network diagram in RAM. And now they don't have to have some very simple idea of how many hops out different directions things are. They just know all the links, and now they can choose an intelligent route. And now they can include the bandwidth of the links. They can choose the fastest route, which might not be the smallest number of hops. So if you have modern routers, you can use that. And modern meaning even anything less than 15 years old, probably. All right, OSPF is the open source free version of this. You can use open source path first. This converges much faster than RIP, and it doesn't create the problem of routing loops. There's proprietary ones like EIGRP, which is Cisco's protocol that does the same thing, but you can only use it if you have Cisco devices. Border Gateway Protocol is what's used on the internet, and this does not count hops, it counts systems, which are basically ISPs. Every large company that has a direct connection to the backbone gets an autonomous system number. So Cloudflare has one, City College does not have one. We're just a customer. Small businesses like this are just a customer of an ISP. But your ISP has an AS number, and so this decides how to move among company networks on the internet with Border Gateway Protocol. And it's considered quite difficult to set up. You only get it, you'll learn how to set this thing up in like the third or fourth Cisco certification. People who know how to set this up are in high demand because it's difficult to set up correctly. How hackable is BGP? It is pretty hackable. It's old and it doesn't use encryption or authentication very much. There have been ideas for years to make a securer form of BGP, but I think it still hasn't happened much. It's considered quite fragile, and it's often manipulated. Several times a year, some country or some device makes a mistake and takes down a large part of the internet. And also there have been a lot of attacks where people deliberately reroute traffic with false BGP methods. It's not very secure at all, but we're all relying on it.
No, it depends on the ISP, they advertise the route.
That's right.
And that's what happened to Russia ISP, and then they put out the route to Apple, and then all the traffic.
That's right.
For Apple route.
Exactly. Yeah, China's done that too, and Czechoslovakia did it at one time by accident, and Iran did it. If you send out bad Border Gateway Protocol updates, then all the global traffic will believe that for a while and go there until people figure out it's wrong and manually block it. It's not. It doesn't have what you'd like, good authentication and stuff. Although people are trying to add that.
On the trust of the user.
Yeah,
ISP, so.
of the network administrators. Yeah. Although people are trying to add some sanity checks to BGP updates and stuff. They're trying to add some security to it, but I think that process is still in its infancy. Let's try another Kahoot. One DEF CON I went to about 10 years ago, a researcher from New York put up BGP updates to route all the traffic from DEF CON through New York for the whole conference and sniff it, and nobody noticed. And then on the last day, presented the results of analyzing all that traffic. So. All right, so which device is at OSI layer 3? Routers. Okay, good. Which device moves packets from a LAN to the internet? That's also a router. That's what routers do. They are your gateways to the internet, to other networks. How they sniff out your network ID even with VPN. I'm not sure about that. You'll have to give me more information, Joe. George, I do not understand the question. All right, what protocol uses hop count as a metric? All right, that's RIP, routing interchange protocol, routing information protocol. Anyway, the old one, RIP, used the hop count. Okay, what's the interior routing protocol that converges rapidly? The more modern one. All right, that's OSPF. Good. All right. All right. Good. All right, good. Yes, there's quite a competition to win the top spot in the Cahoots. That's good. All right, well, let's take a break. It's just 7. Let's take a 10-minute break, and then we'll do some more of this.